Vectors, I don't know about you, but I find it one of the trickiest topics in further maths, just because I don't know, there's so much to kind of get your head around. And then you get questions like this with like a modeling. Actually, I think this one is not as bad as other ones that I've seen, to be fair, but you still have to kind of understand what's going on and apply your knowledge. I've got to say though, it's an incredible topic, like working in 3 dimensions using these ideas of planes and lines. So I'm all for it, of course. Right, we've got 2 birds flying towards their nest, which is in a tree, relative to a fixed origin. The flight path of each bird is modeled by a straight line. And in the model, the equation for the flight path of the first bird is R1. So maybe it's something like this. Now, just a little reminder, we've got our origin here. We get onto the line using our this position vector, and then we go along the line some multiple of this direction vector. But that vector is going to be 2a0. And then the equation for the flight path of the second bird is something like a little bit different, but same sort of form. So now let's say it was up here. So here we're getting onto the line using this position vector, and then we're going along 0, 1, minus 1, just some multiple of that. We're told the angle between the bird's flights is 120 degrees and asked to determine what A is. The reason I've done this is that I can just shift these direction vectors up, and this is the angle between them. So 120, of course, this is not accurate. I've got an obtuse angle here, but don't worry about that. We can still use this idea. But what we need to do is investigate the angle between just the direction vectors. Don't worry about the lines. And we can use the scalar product for this. So A dotted with B is going to be the magnitude of A times the magnitude of B times cos of the angle in between. But we've also got our other version of the dot product, which is AX BX plus AY BY plus AZ BZ. And let's use them both then. So I can write down 2A0, that was meant to be an A, 2A0 dotted with 0, 1, minus 1. Right, well, first up, that is going to equal just A. But using my second definition, well, let's work out the magnitude of each. This one is going to be 2 squared plus A squared square rooted. So the square root of A squared plus 4. And the magnitude of my second one is going to be 1 squared plus minus 1 squared. It's going to be root 2. And then I'm timesing by cos 120. So I'm hoping this is making sense so far. I've drawn my 2 lines. I've shown you how we get onto the lines using the position vectors, and then we've got the direction vectors, which are taking us along the line. And we've said, right, it's those that we need to look at for the angle between the 2 paths. And then I've written down the dot product and done it in 2 different ways, worked it out using this, which just gives us A, and then this version. We've got the magnitudes multiplied together times by cos 120. So I've just got this equation to solve now. Right, well, A is then going to equal root A squared plus 4 times root 2 multiplied by cos 120. And that ends up being minus a half. I'm now going to square both sides. So A squared will then equal A squared plus 4 times 2 times minus a quarter. Oh, sorry, times positive a quarter. So it's going to be a half, which means I can bring a 2 there. Let me just say that one more time. I've squared both sides. So this became 2 times a quarter. It was a half, and then I times the A squared by that. So 2A squared equals A squared plus 4. That means A squared is going to equal 4. So A is plus or minus 2. But only one of these is going to be valid. It doesn't say it has to be positive or negative. However, if we look back, remember when you square an equation, you can create spurious solutions. And if you just check back in here, we need the left-hand side to be negative because the right-hand side is negative. So actually reject 2, a is going to be minus 2. And verify that according to the model, there's a common point on the flight paths of the two birds and find the coordinates of this common point. Of course, I kind of assumed this in the first part, but these could be skew, like this green one could be coming out of the page or something. So you can still find the angle in between them, but now we want to find the common point. Well, we've got our two equations and we want them to have the same position vector. So this is going to be when minus 1 plus 2 lambda, the x value here, is equal to 4, the x value for the second one. We'll come back to solving that in a minute. 5 plus, oh yeah, we know what a is now. Remember, it's minus 2. 5 minus 2 lambda is going to equal minus 1 plus mu. And then finally, 2 is going to equal 3 minus mu. Well, let's take the first one. We're going to get 2 lambda equals 5. So lambda is 5 over 2. And I'll take the third one. I can quickly see that mu is 1. And I'll just check the second one, which I'm just going to label 2. Because I haven't shown that there's a common point yet. Because if I get a contradiction with the middle one, actually there's no solution. You can always solve these kind of simultaneous equations, the top and the bottom, but we just need to check the middle one is also consistent. So then the left-hand side will equal 5 minus 2 times 5 over 2. It's going to be 0. And the right-hand side is going to equal minus 1 plus 1, which is 0. So this is okay. And the lines have a common point. Let's work out what it is. It's going to be easiest because mu is 1. It's going to be easiest to sub back into the bottom one. 4 minus 1, 3 plus just 0, 1 minus 1, which then gives 4, 0, 2. And hence our common point, the coordinates, is going to be 4, 0, 2. Right, so now we're told the position of the nest is modeled as being at this common point, the tree containing the nest is in a park, and the ground level of the park is modeled by the plane with equation 2x minus 3y plus z equals 2. And we're hence asked to determine the shortest point from the nest to the ground level of the park. Well, there is a formula in the formula book which tells you the perpendicular distance of a point to a plane. And that is going to give us the shortest distance. Because think about a plane, think about a point up here. You're not going to go down there, are you? You're going to go directly perpendicular. Now, hopefully you're a bit like me, and when you first saw this equation, and hopefully this is not the first time you've seen this, you thought to yourself, where does that come from? And it's really frustrating to me that the textbook does not explain it. So I'm going to talk through at the end where it comes from, because I think it's one of the most interesting bits. We're doing further maths here. We're not just learning to substitute into a formula, we're learning to see where these formulae come from. So, right, we've got to get our equation in the right form. It's nearly in the right form, but not quite. I just need to minus 2 and set it equal to 0 so that d is actually minus 2 rather than 2. And we've got our alpha, beta, gamma here. Okay, so let's work it out. We've got everything we need. So it's going to be 2 times 4 plus, sorry, then it'll be a 3, won't it? Minus 3 times 0, then plus 1, that's the coefficient of z, 1 times 2, and I'm adding d on, which is minus 2, and dividing by the square root of 2 squared plus minus 3 squared. That's just the same as 3 squared plus 1 squared. So here the minus 2 and the 2 cancel. The 3 times 0 is obviously 0. So this just gives 8 divided by the square root of 14. And that is the shortest distance from the ground to the nest. And to be fair, because we're dealing with a model here, I mean, you get away with it writing it exact, but yeah, we should write it to maybe, three significant figures. 2.14 meters. Finally, we're asked, by considering the model, comment on whether your answer to part C is reliable, giving a reason for your answer. Now, actually, I made a mistake here and got it wrong. I actually looked at my answer and thought, you know what, 2.14 seems quite low, so I think it's not very reliable. But that's not what it's getting at, this question. It says by considering the model, not by considering your answer. So the sorts of things it's looking for is whether you can model the ground using by a plane, whether you can model the flight of two birds using straight lines. And they're the things that you can essentially criticize. So yeah, not reliable as the birds will not fly in a straight line, you could say. Not reliable as the angle between flight paths will not always be 120 degrees. Not reliable as the ground will not be flat or smooth, and the bird's nest will not be a single point. That is the sort of thing it's looking for here. Finally, let's just prove this formula. I have to sort of just remind myself how to do it every now and then because I struggle to do it from scratch without like making a mistake along the way. So we've got ourselves a plane, got an origin here, and we're going to get onto the plane using A. And then we can consider a point in the plane which is going to be R. And we could work out this vector here. So yeah, going this way, that will be R minus A. And then I've got a normal vector. And this is where our equation, so it must be that that vector there is in the plane, that must be perpendicular to the normal vector. So this is equal to 0. So then R dotted with N is going to equal A dotted with N. And that's typically what we then call D. Because if we write down our equation, we're going to get N1x, and N I should say is just N1, N2, N3. Or maybe I should go with NX. Yeah, let's do that. NX. No, they've used 1, sorry, they've used 1 and 2 in the formula, haven't they? So N1x plus N2y plus N3z is going to equal D. And that's our equation of a plane. Okay, it's slightly different to this at the moment because I'm getting minusing D, but don't worry about that for the time being. So now I've got my point here, which I'm going to call X. And then I've got some other points up here, which I'm going to call Y. And this is going to have position vector, or this is going to have coordinates alpha, beta, gamma. So now I can write down the equation of yx. Where I'm going to get onto the line using alpha, beta, gamma here. And then I'm going to be going along some multiple of the normal vector. And then I'm going to look at x. So at point x, I know that this is true and this is true. So I can actually just sub in. Remember, R is x, y, z. So I can replace x by alpha plus n1 lambda. So I'm going to get n1 times alpha plus n1 lambda plus n2 beta plus n2 lambda plus n3 gamma plus n3 lambda. And that is going to equal d. Remember, that is at the point x. And I can rearrange this. So I will get lambda n1 squared plus n2 squared plus n3 squared. And then the other terms, I'm going to subtract the opposite side. I'll get d minus n1 alpha minus n2 beta minus n3 gamma. So that means lambda is going to equal d minus n1 alpha minus n2 beta minus n3 alpha all over n1 squared plus n2 squared plus n3 squared. And we're nearly there. But remember, this is the formula we're trying to show. There's a lot of similarities here. So what I want to do now is work out vector yx, because then we're going to find the magnitude of it. So to get from y to x, I'm actually going to be going this way. So it will be minus alpha minus beta minus gamma, and then adding on that ox that we've just found. So it will be, I've got my equation here. This will just cancel, and it will just be my lambda that I've just found times n1, n2, n3. Right, this is my lambda. So now, finally, if I want to find the magnitude, then it's going to be, well, the modulus of lambda. If it's negative, it's just going to become positive. That's what we're saying here. And then we can use 3D Pythagoras here. So n1 squared is n2 squared plus n3 squared. And if I multiply this and this, then it will end up being, okay, the modulus of d minus n2 alpha minus n2 beta minus n3 alpha all over. So the square root divided by the thing itself, so I will just be dividing then by the square roots. And these are the same, because what we can do is swap all the signs around and you'll still get the same answer here. Now, the only discrepancy is that there's a plus d here and I've got a minus d. But that's just because I've written their d is slightly different to my d, because I had d here. So I would write, mine would be minus d equals 0. So I need to take the negative of that in here, and that's why it will actually become a positive. So sorry, there's a slight discrepancy. You normally write it, well, actually, yeah, there's two different ways you can write it, but yeah, you normally write it like this, and you set it equal to d, but you can make it positive on the left-hand side. Just have to be a bit careful. So not going to go into any more detail on that, but that is an explanation for why it was slightly different. And there we go. That is our derivation. That is the perpendicular distance from a point to a plane, and hence, in our case, the shortest distance from a point to the plane.